All right, let's crack the code on how to really think like a programmer. We're going to build a mental toolkit, the one that experts use to look at a super complex problem and just see the path forward. Let's dive right in. You ever have this feeling? I mean, you've read the book, you get the concepts, you know all the data structures in theory, but then you're staring at a blank screen with a real problem in front of you, and it feels like there's this huge gap between what you know and what you can actually do. It is a super common and super frustrating place to be. And hey, it's not just you. As Jason Koo from MIT puts it, there are these little tricks, these specific ways of thinking that help bridge that gap. And that's exactly what we're going after today, the hidden strategies that turn all that theory into real, practical action. So here's our game plan. We're going to start with that problem-solving gap. Then we're going to tackle 4 different challenges one by one. We'll rank algorithm runtimes, we'll build things with black boxes, we'll try to get the best of both worlds with data structures, and finally, we'll do some surgery on a linked list. Each challenge is going to give us a brand new tool for our final algorithmic toolkit. Okay, let's do it. Let's bridge that gap. We're making the jump from just knowing the stuff to actually doing the thing. And first up on the list, dealing with complexity. So for our first challenge, it's all about speed. You've got a bunch of different algorithms, and you need to figure out which one is the fastest. Now, that's pretty easy when you're comparing something simple like n versus n squared. But what happens when the functions get really, really messy? Exactly. How on earth are you supposed to compare something like 2 to the power of n against n factorial? You can't just eyeball it, and factorials in particular, they grow in this really wild way that's hard to get a feel for. We need a trick. We need a way to simplify things. And here it is, our first tool. It's called Stirling's approximation. Now, don't worry about the crazy formula behind it. You don't need to memorize that. Just think of it as a mathematical cheat code. It lets you take a scary-looking factorial and rewrite it into a form that's way, way easier to handle. The whole point is, it makes a hard problem simple. And just look what happens when we use it. That messy n choose n over 2 function suddenly looks a lot like 2 to the n. And n factorial turns into something we can understand, kind of like n to the power of n. Now we can actually rank them. We can see clearly which function grows the fastest. The n choose n over 2 function grows the slowest, which means it's the most efficient algorithm. N factorial, on the other hand, grows the fastest, making it the least efficient. Just like that, the problem is solved. All right, tool number 1 is in the bag. Let's move on to the next challenge, which is all about a concept called abstraction. The question is, how do you build something new when you're not even allowed to see how your tools work? This is the whole idea of a black box. And in computer science, we do this constantly. We get a tool, say a data structure, and we're told what it can do, like insert an item at the front or delete from the back. But we have no idea how it does it on the inside. All we can use are the functions it gives us, and our job is to build new things using only those public controls. So let's say we need to swap the first and last items. We can't just reach in and move them around. We have to use the tools we were given. So the solution becomes this clever little sequence. First, you use delete last to pull that last item out, and you just hold onto it. Then you use delete first to pull the first item out. Now you've got both. So you just reinsert them in the opposite spots. The last item goes on the front, and the first item goes in the back. And that's it. We just built a totally new capability just by combining the operations we were allowed to use. Okay, on to our third challenge. And this is a classic engineering problem, a real trade-off. It's what happens when you have 2 different tools and each one is great at something the other one is terrible at. The trick is to find a creative way to combine them to get the best of both. And this is the perfect example. On one hand, you have a dynamic array. It lets you jump to any item instantly, super fast. But if you want to add something to the very front, oof, that's really slow. On the other hand, you have a linked list. It's crazy fast for adding or removing things at either end, but if you want to find the 100th item, you have to walk through the first 99 to get there. So how do we get fast access and fast changes at both ends? And the solution is just so elegant. Instead of trying to find one perfect structure, you use 2 simple ones. You take 2 dynamic arrays. The first one holds the front half of your sequence. The second one holds the back half, but you mentally treat it as if it's reversed. Now think about it. Adding to the front of your whole sequence is just adding to the end of that first array. And adding to the back is just adding to the end of the second array. And both of those are fast operations. But wait, you might be thinking, what happens if I keep deleting items from one side and one of the arrays becomes empty? Well, that's where the secret sauce comes in. When that happens, you just pause for a second to rebalance. You take the array that's still full, You split it right down the middle, and now you have two new, nicely balanced arrays. Yeah, that one rebalancing step is slow, but because it only happens after tons and tons of fast operations, the average cost over time is still incredibly low. It's a concept called amortized cost, kind of like spreading out one big payment over many months. Okay, time for our final challenge. And for this one, we're really getting our hands dirty. We're about to perform what I can only describe as surgery on a data structure, carefully manipulating its internal connections, its pointers, with absolute precision. So here's the task. You've got a linked list, and you have to reverse the order of the entire second half. But, and this is a big but, there are rules. You cannot create any new nodes, and you can't use a bunch of extra memory to copy things over. You can only work by rewiring the pointers of the structure that's already there. Now, a problem this tricky feels impossible until you break it down into a plan. So let's make one. It's just 3 steps. First, we just walk through the list until we find the exact middle node. Simple enough. Second, we do the surgery. We go through that second half, and for each node, we change its next pointer so it points backwards to the one that came before it. And finally, step 3, we just stitch everything back together by connecting the end of the first half to the new beginning of our reversed second half. Now that second step, that is where all the focus has to be. It is incredibly delicate work. As you're walking through the list, changing those pointers from pointing forward to pointing backward, you absolutely have to keep track of 3 things at all times: the node you just came from, the node you are currently on, and the node you are going to next. Because if you lose track of that next node, poof, the entire rest of the list is gone forever. It demands meticulous, step-by-step logic. So, we've gone through 4 tough challenges and we came out with 4 clever solutions. But way more importantly, we've uncovered the core strategies, the ways of thinking that were behind them. So let's put it all together. Let's build our toolkit. So here it is. This is your new algorithmic toolkit. First, simplify and conquer. Find tools that turn a hard problem into an easy one. Second, build with abstractions. Don't be afraid to combine simple black box tools to create something powerful and new. And third, use step-by-step logic. When things get delicate, break the operation down into a clear, sequential plan. These aren't just one-off tricks. These are the mental models that expert problem solvers use every single day. And you see, this isn't just about writing code. This is a framework for how to think. It's about simplifying, about abstracting, and about meticulous planning. This is how experts tackle complex systems, whether it's software or something else entirely. So the only real question left is, how are you going to use this toolkit to solve the challenges you're facing?